When you watch a heavy-duty industrial robot smoothly hoist like a 2-ton car chassis, it looks completely effortless. I mean, almost like magic, right?
Right. But underneath that sneak casing, it is the exact opposite of magic.
Yeah.
You're actually looking at violent, massive physical forces being ruthlessly controlled by, well, a symphony of interlocking metal teeth.
Yeah, and today we're tearing up the floorboards on how heavy robotics actually work under the hood. We've got this stack of highly technical R&D notes on precision transmission and gear mechanics for our deep dive today.
And whether you're prepping for a manufacturing meeting or you just, want to know how giant machines don't just tear themselves apart, we are getting into the literal physical mechanisms that make it happen.
Exactly. So let's start right at the center of a planetary gear reducer. In the notes we're looking at, they talk a lot about the sun gear.
Yeah, the sun gear.
I like to think of the sun gear like the center spindle of a vintage carousel. As it turns, it physically forces all the horses or, the planet gears to rotate around it. Is that a fair analogy?
That is a perfect physical model, actually.
Yeah.
And because that sun gear is driving everything else, its concentricity dictates the precision of the entire system.
Concentricity meaning like how perfectly centered and circular its rotation is. What?
Right, exactly. If that center spindle wobbles even a fraction of a millimeter, the outer gears just grind.
Oh, wow. Which actually explains a detail in the R&D specs that totally confused me at first.
The vibration dampening sleeve.
Yes. I initially thought, well, if the gear's geometry is perfectly machined, isn't a sleeve just adding unnecessary bulk to the whole thing?
I mean, it makes sense you'd think that, but it's actually there to cut high-frequency noise in the gearbox's first stage.
Oh, so even perfect gears generate vibrations.
Yeah, exactly. When metal meets metal, you get microscopic vibrations. The sleeve absorbs those high-frequency waves right at the central spindle before they can amplify through the rest of the mechanism.
Okay, so a sleeve handles the vibrations, but what about massive kinetic shock?
Right, the big impact.
Yeah, like if that robot arm drops a 2-ton car chassis, the sheer force would just snap standard gear teeth right off that spindle, wouldn't it?
It absolutely would. And that physical reality forces engineers to ditch traditional gear teeth entirely for those heavy load base axes.
Wait, really? What do they use instead?
They use a pinwheel mechanism, which is inside what's called a cycloidal drive.
Right, right. And unlike standard gears that just grind edge to edge, where, one or two teeth take all the pressure, a cycloidal drive actually wobbles inside a ring, doesn't it?
Precisely. It moves in this eccentric motion, pushing against multiple cylindrical pins, the pinwheel, all at the exact same time.
Oh, it's spreading the force out.
Yeah, because you have 10 or 15 pins sharing the loads simultaneously instead of just two delicate teeth. It gives the system extreme impact resistance.
So if a sudden shock hits, the kinetic energy is distributed across a wide surface area. I get that. But it's not just about surviving shocks, right? It's about generating power in tight spaces.
Oh, absolutely. Like an exoskeleton's hip joint, for example.
Yeah. You need massive torque to lift a human, but you obviously can't strap a whole truck transmission to someone's leg.
No, you have to generate that power efficiently. And engineers solve this using a compound reduction ratio.
A compound reduction ratio, meaning what exactly?
It means physically linking different types of gear systems together sequentially. So you might have a planetary gear handling the high-speed first stage.
Okay, making sense so far.
And then that directly turns a harmonic gear for the second stage. Harmonic gear uses this flexible metal cup that actually deforms to turn the next gear.
Oh, wow. So by compounding them, they multiply the torque exponentially, hitting reduction ratios like 300 to 1 without expanding the physical footprint?
Right. You get massive rotational force out of a very, very compact space.
Wait, I have to push back on the physics of that for a second. If you're generating a 300 to 1 torque ratio inside a tiny hip joint, the pressure on that final output stage would be astronomical.
It is. It really is.
So why doesn't that localized force just shatter the metal?
Well, that is the defining engineering challenge of high torque spaces. And it all comes down to a metric called the load sharing factor.
Load sharing factor.
Yeah. This measures exactly how evenly the mechanical burden is spread across the internal components. If the factor is poor, one gear takes, say, 60% of the force, and it fails prematurely.
Ah, so to prevent that, you engineer a mechanical workaround. The sources actually highlight a floating carrier used for 4 planet gears.
Yes, the floating carrier.
Right, so instead of bolting the gears down rigidly, the carrier is designed to, float or shift just a tiny fraction of a millimeter.
Right, and that microscopic float allows the gears to naturally self-center under pressure.
Oh, that's clever.
It is. The physical force equalizes across all four gears, which gives you an optimized load-sharing factor and saves the mechanism from tearing itself apart.
It's honestly incredible how much flexibility is built into these rigid metal structures. But when we get to the manufacturing floor, who actually verifies that these gears are meeting these microscopic tolerances?
Well, that's governed by the AGMA accuracy grade. That's established by the American Gear Manufacturers Association.
Okay, so there's a strict standard.
Very strict. The higher the grade number, the exponentially stricter the geometric tolerances for the metal.
And the deck specifically highlights internal gears ground to AGMA grade 12. But those weren't for lifting heavy chassis, right? They were for an optical tracking system.
Right. Entirely different application.
So why does a camera need a heavy-duty gear standard?
Because of jitter.
Jitter, like a shaky image.
Exactly. When an optical tracker is zooming in on a target miles away, every imperceptible flaw in the gear tooth's geometry translates to a physical stutter in the camera's movement.
Wow, so even a microscopic bump on the gear messes up the shot.
Yeah. At grade 12, the metal is ground so flawlessly that the mechanical movement becomes perfectly fluid, completely eliminated those microscopic jitters.
That really puts this whole technical vocabulary into perspective. I mean, mastering terms like sun gears, pinwheels, and load-sharing factors isn't just about sounding smart in a meeting.
Definitely not.
It's about understanding the literal physical forces that allow us to manipulate matter with both devastating power and microscopic precision.
Yeah, when you look closely enough, industrial manufacturing is really just humanity finding new ways to enforce our will onto physics.
That is incredibly well said. Which leaves you with this final thought to ponder as we wrap up our deep dive.
Let's hear it.
If we are already grinding metal gears to AGMA grade 12 today, just to keep optical trackers from jittering, what fundamentally new transmission mechanisms are we going to have to invent when our technology requires physical movements that are smaller than a mechanical metal tooth can possibly deliver?